Hello and welcome to the Algorithm Alphabet, a new series that will hopefully both fix my upload schedule and allow us to dive into the wonderful world of algorithms. Or I guess data structures as well, because I'm talking about trees today. Off to a good start. By the way, this series idea comes from the one and only Sebastian Lake, who had it as an unfinished idea and kindly gave me permission to use the format. Thanks Seb, very cool. In general, I'll select topics that are more likely for both of us to learn something through these videos. So for today, let's talk about some self-balancing binary search trees. For the letter A, I'll present and code up the AVL tree and the AA tree, as well as discuss the essential red-black tree in between. Finally, at the end, I'll throw in an even lesser-known self-balancing binary search tree, beloved in competitive programming circles, the FHQ Treap. Let's work our way up through the definitions, starting with a tree. This is a graph structure containing nodes with data, say numbers, and edges connecting these nodes, with the number of edges is exactly one less than the number of nodes. With that constraint, we can see that no cycles can exist, and if we can only travel across each node once, there's only one way to travel between any two nodes. For the tree data structure, and not the tree graph theory, we also need to set a root node. From the root node, we can give our edges direction. Every node except for the root node will have a parent, and every node except for the leaf nodes will have children. This terminology has spawned a myriad of jokes that you probably have seen. Basic tree terminology done. The easiest trees to implement are binary trees, where each node has a maximum of 2 children, the left child and the right child. A binary search tree, then, is a binary tree with its nodes arranged in such a way that, if you look at the values stored at each node, all the nodes in the left subtree have smaller values, and all the nodes in the right subtree have larger values. To be technical, the node labels for an in-order traversal are strictly increasing. This regular structure lends itself very well to recursion because any subtree of a binary search tree is a binary search tree. It's important to note that the arrangement of nodes and edges is not unique, and it depends on the order in which the nodes are added. These two trees look wildly different. In particular, one has height 4 and the other has height 6. Clearly, for searching, one of them is better than the other, so we want to limit the height so that, on average, we don't need to traverse as many nodes down when doing operations. A self-balancing binary search tree, then, is one that automatically corrects and readjusts itself with some criteria to keep its height small by not having too many nodes on the left or right subtrees. It balances their heights. This means having more nodes at each layer, and it's possible to keep the height of the tree with n nodes at just O of log n. The first self-balancing binary search tree proposed was the AVL tree, invented in 1962 by these two Soviet mathematicians, and the condition that AVL trees maintain to keep themselves balanced, called the invariant, is the height invariant. At every node on the tree, the difference in heights between the right and left subtrees, called the balancing factor, is kept to no more than 1 and no less than -1. Take this tree for example. It has overall height 3 and all the nodes have balancing factor 0. Let's add a node on the right and see how the balancing factor changes. The tree is still in balance. How about we add another one under the one we just added? Clearly, this tree has become unbalanced, with some balancing factors being 2. However, visually we can see that it's not too difficult to fix. All we have to do is swap the order of these two nodes. We now have to figure out how to do this in general. The fundamental operation invented, which is used a lot, is tree rotation. It's an operation that changes subtree heights while making sure that all the nodes are still in the right order, so we can still keep it as a binary search tree. There are 2 directions of tree rotation, left and right, just like clockwise and anti-clockwise. Here's a left rotation applied at this node. And here's a right rotation on this node, which returns our tree to how it was before. Let's watch that again a couple more times. Convince yourself that the tree stays a binary search tree before and after, and only the heights of the subtrees change. Let's write the left and right rotations in code. First of all, for a node class, we store its label and the height of its subtree. Also, we store pointers to their left and right children. These two helper functions allow us to update the height of our nodes. Here's the right rotation function. It takes in a pointer to the root y of the subtree being rotated, switches some children, updates some heights, and then returns a pointer to the new root of that subtree, x. The left rotation is identical. AVL rebalancing could seem tedious at first, since there's a lot of cases to consider, but that doesn't make it hard to understand. Let's think about a single operation, node insertion. Going back to our height invariant, for balanced AVL tree, the balance factors are all 0 or plus or minus 1. If we add a node and suddenly some of our nodes have a balancing factor of plus or minus 2, then they are unbalanced. Note that all these unbalanced nodes are always ancestors of the new node, as their subtrees are the only ones that are altered. However, this doesn't mean that we have to rebalance for all these ancestors, as we saw earlier. Since the difference between any two adjacent subtrees is 1, all the leaf nodes of adjacent subtrees should have heights, say, h and h plus 1. As soon as we get a node of height h plus 2, we just need to put it on the h plus 1th layer, and this will fix the balancing for all subtrees. Specifically, we only need to deal with the deepest unbalanced node. Since the balancing factor being plus 2 and minus 2 are symmetric cases, let's consider when the right subtree is taller than the left one, which we can describe as right-heavy with a balance factor of plus 2. There's two ways this could happen. Either the right-right subtree or the right-left subtree gets a height of h plus 2. For the first case, it's a single left rotation on the problem node that does the job. This makes all the subtrees have height h plus 1 and is known as the right-right case, as starting from the unbalanced node, the deepest subtree is reached by traveling right twice. For the second case, we need to look at even more subtrees, which I'll shuffle around in our rotation. It doesn't matter which of these has height h plus 2 and our procedure works either way. The procedure is a right rotation on the right child and then a left rotation on the problem node. This is called the right-left case. To reach the deepest subtrees from the unbalanced node, you travel right and then left. When the imbalance is left-heavy, we have the mirror image, a left-left case and a left-right case. Let's put node insertion into code. This is done with a recursive function that, when traversing down, finds where to place the node, and when traversing up, balances the tree. Since the root may be changed after rebalancing, the function also returns a pointer to the new root after all the rotations are done. The top half is all about finding where to put the new node. In the bottom half, I've labeled all the cases that our tree could end up in. Deletion is more of the same story. Again, we have a recursive function that traverses down to find the node to be deleted, and then traverses up doing necessary balancing work. If the node we're deleting has two children, we use the trick, which we're going to use frequently, of replacing it with the next largest node in value. This node then has at most one child because we get to it by traversing right once and then left until we can't anymore, allowing us to convert to the next two cases where the node to be deleted has just one or no children. If we delete a leaf node, we can get rid of it without any worries, and if it only has one child, we can also simply move that child's subtree up. After we've removed the node, returning from our recursion, we have the same balancing checks from insertion. That's it for addition and deletion. Because AVL trees are very strict in their height control, in fact here's a proof of bounds on screen right now, the constant factor in the O of log n height is very small. meaning that they are the preferred choice when reads and searches are frequent. Since this is a balanced binary search tree video, there is no chance I'd be let off without talking about red-black trees, the most general use tree we have. If you look at just about every introduction of this tree though, you'll probably find, like I did, that the rules for maintaining this tree seem completely arbitrarily chosen. So hopefully you'll get some insight here into how these trees came into existence. But before that, what even are the rules and invariants? First, every node is colored either red or black. Second, all null nodes, so empty children, are colored black. By convention the root is black, but it really doesn't matter. The red-black tree has two invariants. The red invariant says that a red node does not have a red child, and the black invariant says that every path from the root to a null node goes through the same number of black nodes, which is called the black height. Yeah, completely unintuitive conditions. So let's step back for a second. If we read closely on the Wikipedia page, we might notice it says that red-black trees are similar in structure to 2-3-4 trees. What's a 2-3-4 tree? First, what's a 2 tree? Just another way of describing a binary tree. Next, what's a 2-3 tree? Instead of each node having just one label and 2 children, it could also have 2 labels and 3 children. A 3 node. A 2-3 tree is a mixture of 2 nodes and 3 nodes. Also, it has the additional requirement that it's perfectly balanced, so all leaves are at the same depth. Here's an example of that. Two 3-4 trees are an even further extension, including 4 nodes with 3 labels and 4 children. Of course we could extend this further, and in general there exist B trees with nodes having a maximum of B children. Since these trees force all leaves at the same level, the maximum height is O log base B of n, so they're a form of balanced search trees. A problem is that these trees are complicated to deal with, since they have a few different node structures, which leads to the creation of red-black trees. Instead of having multiple labels at one node, we can blow up each 3 node or 4 node into multiple nodes, and then color the additional nodes to show that they were once part of a bigger node. And so, it's a miracle. Red-black trees are just an easy way of implementing these nodes as a binary tree, no need for any fancy splitting or merging of nodes. As each tree is made from linking these 2, 3, and 4 nodes together, no 2 consecutive red nodes can occur, which is the red invariant. And since a 2-3-4 tree forces all leaves to be at the same level, the path in a 2-3-4 tree from the root to each leaf goes through the same number of nodes, which translates the black invariant for a red-black tree, since each 2-3-4 node translates to exactly 1 black node. Since these trees aren't the main focus of the video, I'll go through the insertion cases quickly and skip deletion since it's quite complicated. Each new node is red by default. Note also that it's not a one-to-one correspondence between 2-3-4 trees and red-black trees. A 3 node can be interpreted as either a left or a red-right child. A variant that simplifies the code is the left-leaning red-black tree, where all 3 nodes are represented by a left red node. Another variant that corresponds to a 2-3 tree instead of a 2-3-4 tree is our next tree, the AA tree. Instead of representing large nodes with colors, we use levels, which are similar to tree depth. A 3 node will be represented by 2 nodes at the same level, where the edge between them always points right, immediately halving the cases we have to work through. This means that the left child also has a level 1 less than its parent, but the right child could have a level 1 less than or equal to its parent. Since the largest node is a 3 node which has 2 labels, no 3 consecutive nodes can be at the same depth. When we insert a node to guarantee the 2-3 tree property that all leaves are at the same level, each new leaf begins at level 1. For convenience, we'll create a global bottom node at level 0 that all leaf nodes point to. So what happens if it's a left child, which isn't allowed? We can do an operation called skew, which is really a right rotation in disguise. Check out the code. Notice how there's a bunch of if statements to detect if this function should actually trigger, so if we can't skew a node, nothing happens. So we've removed a possible left horizontal edge. But then what happens if this causes 3 consecutive nodes to be on the same level? This is equivalent to having a 4 node, which we split into 2 nodes with the split operation. This is more like a left rotation, and it increases the level of the middle node by 1. This is the code, and again notice the checks that are in place. Therefore, after inserting the node, at each level we first skew then split our root before moving up. The elegance of AA trees is in its simplicity. We just saw how we can apply the same combination of operations in all cases of insertion rebalancing, and such is the case during deletion. Let's see what happens. As before, we will use the replacement trick, where if the node to be deleted has 2 children, we replace it with the next largest node instead, which is guaranteed to be a leaf. Leaves are easy to get rid of, we don't need to do anything. This could create a 2-level gap between the current node and the child of the deleted node, which means we'll have to pull the parent down a level to settle the violation. If the parent also has a right child, we'll need to bring it down as well. In other cases, our node would get pulled down to create a left horizontal edge, requiring a skew on the root. In the absolute worst case, the nodes are arranged looking like so, and we'll have to skew twice more on the right of the root and on the right of the right of the root to get rid of all left horizontal edges. This gives us a chain of 6. Finally, splitting twice on the root and then the right child of the root to send 2 nodes up gets the job done. Therefore, here's our final delete procedure. Decrease the level, then do 3 skews and 2 splits at each level. There we go, we finished up the 2 A trees for the first letter of the alphabet. It's time to spin things up a little. Or not, because the final tree today doesn't involve rotations. It's known as the non-rotation Treap, the FHQ Treap after its inventor Fan Haoqiang, or even just Treap in the competitive programming community. During programming contests, it's important that your code is not just fast, but short and simple to reduce the possibility of mistakes, and this data structure checks all the boxes. A treap is just a binary search tree smushed together with a heap, and so nodes have to fulfill the properties of both. In a heap, each node is given a random priority value, and the priorities of the children must be lower than the priorities of the parent, which is the main control of the arrangement of nodes. Unlike self-balancing BSTs, the randomization means treeps are not guaranteed to have O of log n height, and in the worst case, operations could take O of n. In reality, the probability of the nodes aligning is very small, and the lower constant factors and elegance mean they are still sometimes used. Instead of rotating, the FHQ Treap uses splitting and merging. Splitting allows us to break a tree into a left and right subtree, where all nodes in the left subtree are not greater than a specified value to split by. The split function takes the current node, a value which it splits by, and 2 numbers that are crucially passed by reference, which are updated during recursion to become the 2 roots of the subtrees. If the current node's value is greater than the value to be split by, then the current node and its right subtree will all belong to the overall right tree, so we continue our recursion with the left subtree. The right edge of our current node is fine, but our left edge could be changed, so we need to transfer it to the root of the left subtree in the next step. Similarly, if the current node's value is not greater, then it as well as its left subtree belongs in the overall left tree, and we pass on the right edge to be updated. Pretty neat. How about the merge function? Well, since it's meant to be used in conjunction with the split function, it assumes that the two trees that are input have keys belonging to disjoint intervals. Now, let's assume that the root of the right tree has a higher priority than the root of the left tree. Then, by necessity of a heap, it must be the overall root of the new tree. After that, we can recurse down and merge the left subtree of the right tree with the left tree. The mirror case is again identical. So how do we insert into this tree with split and merge? We'll have to merge the new node in, which means that we'll need to split the tree by that value to ensure we get a subtree with all nodes less than the value, which is on the left. After that, we can merge the new node with the left subtree, and then merge the resulting subtree with the right subtree. This literally takes 6 lines of code, which is hard to get wrong if you know how everything works. How about deletion? Well, we can first split out all the nodes less than the node to be deleted, and then in the right subtree, split out all the nodes greater, and then merge the two subtrees which don't contain the node we want deleted. In the spirit of competitive programming, let's solve a pretty difficult problem with this data structure to understand even more about this tree, which should be pretty exciting. Here it is. An array has n elements, all initially 0. M operations are applied, and each one is of 3 types. The first is a range add operation. 3 integers are given, the first 2 are the endpoints of the interval, and the third is the number you add to each element in that interval. The second is a reverse operation. Given the endpoints of an interval, reverse the order of the elements. The third is a maximum query operation. Given the endpoints of an interval, print the maximum element in that interval. This is nasty. We have to maintain an array undergoing these operations, which are not the easiest to deal with. Specifically, the reverse operation prevents us from using another data structure, the segment tree, to easily take care of this problem. However, we can learn from the segment tree when applying the FHQ Treap here in a clever way. To solve this problem, 2 key tricks need to be identified. The first is not to store the value of each element as the node label, but the index of the element in an array. This will let us be able to split out a specific interval to operate on, just like how the problem asks. But how? With the reversing going around, we can't just store an index, it'll get changed. But we can store the size of the subtrees of each node. If we want the 6th element, we want the 6th node from the left of the tree. Suppose the left subtree contains just 3 nodes, then including the root that's just 4 nodes. So then, the 6th node must be the 2nd node on the right subtree, so we shift the recursion to the right. Writing this up in code, our new split by position function looks like this. What's this push-up function doing here? It updates a current node's information after its children have been updated. For this problem, it updates the size of the node subtree, as well as the maximum value in that node subtree. The merge function doesn't have any changes to its logic, but also has this push-up function attached to the end. On to the second key trick, which is to add lazy propagation tags. The key idea is to be lazy. We know we have to add 4 to all nodes in this node subtree, but we don't want to. We'll just keep track by adding 4 to an indicator or tag to show we should probably deal with this in the future. Oh look, seems like we'll have to subtract 1 from all nodes in the subtree now. We're still lazy, so guess we can just subtract 1 from the lazy tag instead. Oh no, we have to split the tree. The children may not be the same ones after we merge back, so whatever shall we do? This is the propagation in lazy propagation. We can write a push-down function that, whenever children are being rearranged, we can transfer the lazy information from the current node to its children, so they can be separated from the parent. For this problem, we need 2 tags, one for addition and one for reversing, so the push-down function looks like this. Let's put all the pieces together and finally solve this problem. I hope you enjoyed this video, and I'll see you in the next episode. Thanks for watching.